We're going to do this activity where we're going to see how fast we can, the number of beans can go from this cup to this cup. So we start with 1, and every time we roll it out on the plate, if it's blue, then we're going to add another one. So we did 1 try, and already we did not get a blue one. So we're going to try it again. Still is not blue. And now it's blue. So since it's blue, we're going to add another bean to our cup, and we're going to see how many times it takes before we get a lot. I have another blue side, so now I'm going to add another bean to this cup here. And we're going to see how fast this takes to grow. 2 of them have the blue side up, so I'm going to add 2 more beans. So already this is growing pretty fast. Let's see if we can do this in like 30 seconds. Okay, so 2 are blues. I'm going to add 2 more beans to this cup over here. And now we're up to, I don't know, 7? Something like that. Even more than 7. 1, 2. So we're going to add 2 more to the cup. And we're going to keep repeating the process. So the reason why I'm doing this is because we have these 2 goofballs named Fiona and Gregoire, and they're trying to they did this trial, and then they created an equation. And whoa, this one, 1, 2, 3, 4, 5, 6. So we're going to add 6 of these. 1, 2, 3, 4, 5, 6. So Fiona and Gregoire both made a function that represented the number of beans they had. And already, this is growing really fast now. 1, 2, 3, 4, 5, 6, 7. Oh goodness. 1, 2, 3, 4, 5, 6, 7. And then, now, once they figure out their trials and they make their equation, we are going to, oh my goodness, there's so many. We're going to, let me finish my thought. Figure out how many times it takes for them to get 100 of these beans, or 500, or 5,000. We don't have 5,000 here, but let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19. I had to add 19 of these. Oh gosh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, now I have to add all of these back in here. And we have to see. Oh no, I lost one. Oh no, this is chaos. And now we just have a lot more. We started with 1, and now a few minutes later, oh gosh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Oh gosh, I have to add 22. So, oh no, I dropped one. So the point is, these add up really fast, and I'm going to try to count while I talk. I'm just guessing. All right, 22. And now what we can do is actually we can create a model involving an exponential function. And then from this model, we can now calculate the number of trials it takes to get to a really big number. Because I'm not going to sit here and count out 5,000 of these beans. So we're going to create a model and use our model and our knowledge of exponent properties and figure out how to count a lot of numbers without actually having to count a lot of numbers. And that's it. Now that we've previewed the bean counting incident, let's go look at Fiona and Gregoire's equations that they came up with. So Fiona and Gregoire did the same thing where they would roll out the beans, and then every time a blue side came up, they would add that many more into their cup, and they would watch how fast the amount of beans in their cup would grow. So Fiona came up with a equation that represented the number of beans in the cup, and it looks like this. It's f of t, and then Gregoire, he came up with one. It's g of t. Now, the first question in this video, you're going to need your calculator, and in class tomorrow, you're going to need your calculator. So if you need to pause right here, go get it. Otherwise, I'm going to attempt to use one on the screen. So exercise 1, this is from lesson 24A. Without doing any calculating, determine which student, Fiona or Gregoire, accumulated 100 beans first, and then explain how you know. Let's take a look at this a little closer. Let's just look at the general equation for an exponential equation. We have A, which is the scaling factor, and then we have B, which is the base. And the base in this case is going to be the main component that tells you how fast this function is going to grow. You can tell if a function is going to grow faster just looking at this base. So in both Fiona and Gregoire's equation, they have a coefficient A, a coefficient. You can add that in your vocab list. Coefficient A and a base B. If you have a higher base, your function's going to grow faster. So let's take a look. Fiona B is 1.357, and Gregoire, the B value, the base for Gregoire, is equal to 1.629. So it looks like that Gregoire's function is going to grow faster just based off of the fact that his base is bigger. But look how the coefficient for Fiona is bigger than Gregoire's coefficient, so maybe it won't change. Let's find out. Let's do the math calculations to find out. Using Fiona's model, okay, that's this one highlighted in yellow. How many trials would be needed for her to accumulate 100 beans? When I read that, total 100 beans, I think 100 is equal to f of t. That's equal to the y value. So I'm going to take 100, and I'm going to set it equal to 1.263, 1.357 t. Now, using your good log skills, your log skills, we are going to solve for t. When t is in the variable, before how we've solved it is we tried to match a base and then set the exponents equal, because if we knew that the bases were equal, then we knew the exponents were equal. But look, we can't do that. And we purposely pick these problems because all these decimals means you can't do that. So how do we solve this? So we want to isolate bt. So we're going to divide 1.263, divide both sides 1.263. So if I do that, then 100 divided by 1.263, that's going to give me 79.176. Okay, 79.176 is equal to 1. I'm leaving a space right here on purpose, 1.357 to the t power. Now, this is how you are able to solve for the t in the exponent. When a variable's in the exponent, you take the log of both sides, log. Yay. So let's take the log of this side. The right-hand side, we can move this t to the front because that's one of our log properties. Log of 1.357. And this is going to be log of 79.176. So let's do that. Let's take the log this side, 1.898. 8 is equal to t times log of 137. 1.357 log 0.132. Okay, I'm multiplying. This means multiplication. So now, how do I undo 0.132 times t? Well, you divide. Divide. So I'm going to take this now and punch that into my calculator. I don't remember what it said. Okay, 1.898. 1.898 divided by 0.132 equals 14.37. T equals 14.37. So it took her 15 trials, 15 times she dumped out the cup and put beans in and dumped it out before she got to 100. I think I beat her in my trial in the video you saw. How many trials would it need for her to accumulate to 1,000 beans? So we're going to do the same thing, except instead of 100, we are going to calculate to 1,000. 1, 2, 3 equals 1.263, 1.357. T. Go decimals. To solve for t in the variable, we need to isolate this bt. So we have y equals a b to the t. You need to isolate before you take the log of it. Oh. Now, like from here, you can take the log. Okay. Divide. I'm going to punch this in my calculator right now. Okay, 791. That makes sense. 791.765. Yep. Okay. Equals 1 point. Oh, I'm going to leave a space. I'm strategically leaving a space. Because I'm going to take the log of both sides. Because I want to get this t down here so I can solve for it. So I'm going to take the log of both sides. Log. Okay, so I'm going to take the log of this. Oh, I pushed the wrong button. Too bad. 791.765 log 2.89. 8. Oh, it looks the same. Oh no. And then t is equal to, I'm going to multiply these two, or I'm going to find, because remember, log of a decimal is just another decimal. So now I have 1.357 log. Did I take the log already? 0.132. And now I can divide both sides by 0.132. 2.898. 21. 21.85. Okay, that means she took about 22 trials to get to 1,000. We're going to do the same thing, but we're going to use Gregoire's equation in the next video. So if you needed help solving for logs or you had trouble following with your calculator, then that's where you make a little note. Otherwise, we're going to move on to the next part. I'm going to pause it right here, though.